Let's get started for our remote presenters. I'm Andrew Howard, co-chair of the Asia Pacific Research Platform. I'm also Associate Director of Cloud Services at the National Computational Infrastructure in Canberra. I'll be starting off with a very brief introduction to some of the projects that we're running at the National Computational Infrastructure and our participation in APRP. So thank you for joining us. I'd like to start by acknowledging and celebrating the traditional peoples on whose lands we meet and pay our respects to elders past, present and emerging. First of all, I'd like to start with a very brief advertisement for Supercomputing Asia 2024, which NCI will be hosting in Singapore, in Australia in February next year. We'll have dozens of exhibitors, around 1,200 participants. We'll be holding it at the Sydney Convention Centre, and we invite you to hop on down to Supercomputing Asia 2024. Our world is joined by a large number of network services operated by our research and education communities. This map shows just some of the fibers and network paths that connect us together. And for those of you who joined the routing working group yesterday, there's a lot of work in terms of working to optimize the best paths across these networks. NCI is one of Australia's Tier 1 high-performance computing centres. We directly support around 8,000 Australian researchers and researchers from around the Asia-Pacific region and around the world. We're Australia's fastest supercomputer, coming in at about 9.26 petaflops. NCI is funded by a variety of schemes, including the Australian federal government, our national science and research agencies, the Bureau of Meteorology, and Geoscience Australia. We support the entire spectrum of science, fundamental, strategic, applied, and industrial. For every dollar that the Australian government contributes to NCI, we return $2.22 of national value. So we almost double the contribution in terms of return on investment for our government. Australia has two Tier 1 high-performance computing centres, NCI in Canberra, Australia on the East Coast, and on our West Coast, our sister centre, the Pawsey Supercomputer Centre. Both centres provide supercomputing, HPC, cloud, data and analytics, and community outreach and training. Our high-performance supercomputer, Gardi, has around 155,000 cores, 756 terabytes of memory, and 640 GPUs of various ages ranging from A100 upwards. We're also experimenting on next-generation GPU technologies from a variety of vendors. My area runs the Niran Cloud. Niran is from one of the Australian Aboriginal words for the edge. We repurposed our former high-performance computing system to be a massive research cloud, which we're able to offer to the Australian and Asia-Pacific research communities. This occupies around 22 racks. It is an OpenStack-based system. We've got around 42,000 Sandy Bridge processors, around 1,440 Broadwell processors. We're about to supplement this with around 5 to 6 racks of Skylake processors, which are being retired out of our Gardi supercomputer. Our sister supercomputer centre in Pawsey also has their cloud called Nimbus. Just to show you where each of the centres is located and the network connections that support our operations. We run an environment called Australian Research Environments, or ARE, which is based on a product called Open On Demand. This provides a friction-free way of anybody to use our supercomputing facilities from a simple web-based interface and contains pre-packaged application services which are discipline-specific. So we package for our bioinformaticians all of the bioinformatics tools into containers, which can be run on either our cloud or our high-performance system, Gardi. We're involved in a number of national projects. We support the Galaxy Australia Hub, the National Centre for Indigenous Genomics, our Australian research environments, and ARCOS, which is the Australian Container Reference Organisation. In 2023, we've got a number of really interesting projects going on. We'll be adding additional resources to our cloud with 3 racks of Skylakes. Kubernetes is something which has been highly demanded, which we've been working on for several months. And we'll be announcing our Soft Iron Centre of Excellence in the coming weeks. We've seen an increasing demand for Kubernetes. We've been doing proof of concept on Kubernetes variants. We've stood up K3S in tenancy for Kubernetes environments. And we're currently experimenting with both Rancher and more recently Harvester. Our collaboration with Soft Iron provides a sovereign supply chain for us, which allows us to run high security applications with data privacy requirements, particularly in the biomedical space. Soft Iron is a modular system, so you can just dynamically add nodes into their cluster. NCI is heavily involved in data capture and data storage. We combine our cloud, high performance computing and storage into a triangle where all of the elements are accessible from each of the other elements. We also have a number of other projects, our National Cryo-Electron Microscopy Virtual Laboratory Facility, our Australian research environments, building more additional discipline-specific areas with tools optimized for each discipline and optimized for running on all of our platforms. And we provide a common container environment which can run across our HPC and cloud environment. So users can start on the cloud and as their computational needs grow, move to HPC capabilities. One of the most exciting projects we have running this year is Prospect, which is revolutionizing cancer treatment with precision medicine. We'll be sequencing 20,000 people in 2023-24, with an expansion to 40,000 sequences in 2024-25. The idea is to match patients with new drugs, treatment, personalized medicine. Some of the challenges are that our health departments are state-based, which has differences in legislative frameworks. We need to provide a secure data transfer facility from 19 state-based pathology services, providing privacy and data security, managing a consent framework, both pre and post-mortem, and maintaining a very large data storage volume. And our risks are data leakage or exposure and the exposure of personal private information. Prospect is a closed research environment. We keep the data locked in. The researchers bring their workflows to us, we run them, and we return the results. We also hold a number of reference data collections across pretty much every field of science. As one of our previous speakers mentioned, data is absolutely key for AI, providing fair care and other principles, but most importantly, high-speed access to that data so that people are not wasting valuable compute resources. That's a very brief overview of NCI. Thank you very much. If you'd like to get in contact with me, please reach out. I'm on Hoover, or you can join us at any time in the APRP working group. So, without further ado, I'd like to hand over to our next speaker, who is Kiwok Kim from KISTI. Kiwok, could you share your screen, please? Kiwok, can you hear me? Kiwok. While we wait, does anyone have any questions so far on any of the presentations that you've seen today? There we go. Keyworks Online. Over to you. Keyword, ready to proceed?
Yeah. Can you hear my voice?
Yep, and we can see your slides as well. Thank you.
Yeah. You can see my slide?
Yes.
Yes, I'll start my presentation. Hello, everyone. I'm Giuk Kim, working at KIST. I'm very glad to present my work here today. My research scope is 60 gigahertz wireless data transmission infrastructure since last year, and I'll give a presentation about that research. At the APRP working group session at the March this year, I introduced the wireless data transmission project of KIST. This page summarizes what I explained at the time. We've been working on scientific data collection using IoT since 2018, and last year we extended to the study of millimeter wave and sub-terahertz-based scientific data transmission. The 60 gigahertz frequency has features with low radio interference and enhanced radio security, and its unlicensed frequency band assigned by each country has bandwidth exceeds 8 gigahertz, so we can achieve very high throughput with it. And additionally, the 60 gigahertz band is the frequency used by WiGig standard, so we can easily get commercial radio devices of 60 gigahertz in the device market. And I also said in the last session that a set of 60 gigahertz mid-range radio rings between KIST buildings are under construction. Now the construction is done, so I'm going to show you the construction process and the results. First, we participated in a project to receive funds for the construction. Within this project, KIST's role is to create a test bed for a wireless smart building environment and test data safety zone based on SDN network separation. We build wireless network in two objectives. The 60 gigahertz wireless network is used to build wireless links between buildings as a part of the backbone network. Our backbone network connects servers located in different buildings by end-to-end controllable SDN network. The 60 gigahertz radio connects the sections between each building rooftops in the air. The air between building rooftops is the best environment for using 60 gigahertz equipment because the line of sight is guaranteed in here because people or others do not pass by the air. And we also use Wi-Fi devices for wireless access of test nodes. I think there is no need to explain what is the access network using Wi-Fi. And we will test some robots or AGVs as a test node. So using this wireless access network. This is our construction procedure. First, 4 60 gigahertz wireless equipment were installed in each building. Next, communication boxes are installed next to the 60 GHz equipment in each building, and we did optical cabling construction. It connects each communication box to the backbone network switch. And finally, we installed indoor and outdoor Wi-Fi equipment for wireless access. The total construction period took about 2 months, and I'll show you each procedure in more detail on the next pages. This is the radio equipment we use to build a 60 GHz wireless link. It has an independent radios on each side, so it has 4 radios. So it is originally a device that can communicate in 4 directions. However, since we will use only one direction facing each other between the 2 buildings, so we activated only one radio per equipment. And another thing to point out is that it's a device with 3.8 gigabps of bidirectional aggregated throughput per radio in specification. This means that 1.9 gigabps is the maximum throughput in spec when you send traffic in one direction. I'll show you the end-to-end traffic throughput test results at the end of the presentation, and you can see that is almost close to this max throughput. And we installed 4 of these 60 GHz equipments were in each building. In order to install it high enough not to be blocked by the wall, so we had to set up the steel pipe stand, as you can see in the picture. And second, these are our communication box. The box contains devices to provide power and network connectivity to 60 GHz equipment and outdoor Wi-Fi equipment. And we designed the network cabling of the boxes and radio equipment in this way. And we did optical cabling construction. The red and green lines are the sections where new optical cables are installed. So through this cabling, the data plane and control plane for the SDN backbone network were constructed, as shown in this picture. The wireless links belong to the data plane. And these are pictures of fiber cabling construction. And the Wi-Fi APs for test terminal access, we will be explained in indoors and outdoors. For indoor Wi-Fi APs were installed in the office of the Kisti Creative Center. And this is pictures of indoor Wi-Fi. And we also installed outdoor Wi-Fi APs in these 6 points. These are pictures of outdoor Wi-Fi AP construction, and you can see that the antenna is installed at an angle so that it can communicate with test nodes below the wall. And is the result of our construction. And this is end-to-end throughput test results. 2 servers are located in different buildings were connected on SDN controllers, and traffic was flowed, and it passes through 60 GHz wireless links between buildings, as you can see, but the wireless equipments are not visible in this controller because they are not SDN controller equipment. So I pointed that in this picture. And anyway, the test results show 1.63 gigabps on a rainy day and 1.79 on a sunny day. As explained earlier, the maximum throughput according to the specification of the equipment is 1.9 gigabps, and you can see that the speed does not increase does not decrease significantly even when it rains. If we aggregate the 4 wireless links we built and assume two-way communication, then we could show results of more than 10 Gbps throughput. This is future work. In fact, my role ended in building a wireless infrastructure, but I can tell you one plan to test on this infrastructure. It uses HVO robot to transmit real-time video throughput. The HVO robot transmits real-time video through wireless communication while moving in outdoor spaces. Then the remote server analyzes the video and control the robot remotely. Thank you. It is my work done in this year.
Thank you very much. A very fascinating presentation. Thank you. Okay.
high-speed network, we can call it big data superhighway. In the near future, it's just a term, wireless big data superhighway. And so many places, the isolation tool is without the wireless network. You can construction, you can deploy the wireless technology. So the 5G industry, the wireless sensor, the IoT sensor, and all of these areas we combine our research platform area. You can understand the presentation.
Thanks, Roshan. Our next presenter is Noor Asila, who will be talking to us about distributed high-performance computing in Malaysia and delivering the Malaysian country update. Over to you, Asila.
Okay, thank you, Howard. Thank you, Andrew. So can you hear my voice and my screen?
Loud and clear.
Okay, thank you so much, Andrew. Okay, hi everyone. My name is Noor Asila. I'm from University Putra, Malaysia. And today I'm going to update about the project for the distributed high bandwidth HPC. So I'm representing one of the team from Malaysia. So I believe everyone has listened to Dr. Jong-hoon Kim and Dr. Asif and Dr. Asif Han regarding this project. So I'll skip the introduction. So basically, this is all the activities we have done, especially in Malaysia. So the project started in April 2022. We have several online meetings, and then we have meeting during the APAN 54, also including in the meetings. And then last year in December, the members come to Malaysia, Dr. Jong-hoon and Kim. We have the MOU ceremony, system setup, and some discussion. So you can see some of the photos. And in February 2023, again, we have discussions during the APAN 55. And recently in June 2023, we have the international conference for the high bandwidth distributed HPC. And we are so lucky to have the 1 master node and 3 worker node for this project, which help us a lot in our limitations of HPC resources. So this is actually the conference that jointly organized by University Putra and also KISTI and sponsored by the Asia Connect and TN. So it held in 21 to 22nd June 2023. And this is some of the programs. So we have speakers from KISTI, from the Korea, and then of course from UPM. So from various field, the computational chemistries, agricultures, engineerings, and interestingly, we managed to organize the hands-on workshop, which conducted by Dr. Asif Raza for the beginners, how to use the platform. So we have many various background participants from the computational chemistry, bioinformatics, agriculture. So I can say it's a successful workshop, and it is very interesting. Many people looking forward, many researchers looking forward to use this platform eagerly. And secondly, we have the hands-on workshop, how to manage the platform, which focus for the network engineer and organized by Mr. Kim. So this is some of the photos during the workshop. So the hands-on is actually conducted by Dr. Asif from remotely. We also have some visits near the Putrajaya. So I believe everyone has heard what Dr. Fiza's, and Dr. Fiza is my colleague. So just now she presented about the sequencings and how the limitations of the HPC in UPM, I mean focusing in UPM, but in general in Malaysia. So the limitation is actually costs us quite a lot of money, where, for example, like Dr. Fiza, she has to pay the industry to do the data analytic. And we want to thank you for this project, which reduces our limitations on these HPC resource problems. So this is our previous HPC. So it's quite, it's not quite, but it's quite, it's very old. So we assembled in 2012, and it's already outdated. And this is like a very example of our common practice, where most of us will purchase like the HPC just enough for our project. But this one is quite survived. Many users using it since it has one GPU V100. So it's quite a waste of money because everyone buying their own. However, it is very hard for us to convince and to get a centralized HPC for our universities. So we put a lot of effort, for example, proposals for the 12 Malaysia plan, and from our university's budget, but it's still in progressing. We also organize quite many HPC workshop for the awareness, like maybe starting 2005 until today, but there's a gap in several years between 2013 and 2019. This is some of the poster in our HPC workshop. One of the renowned speakers that we managed to invite is Professor Dr. D.K. Panda for our HPC workshop in 2021. And we also organize like the Python workshop, for example, for the data analytics. And this is some of the talks from our users. I mean, the users for HPC from agriculture is very interesting. From AI, the bioinformatics from Dr. Fiza, computational chemistry, and then this is from engineering regarding the biomimetics. So all these are the users that really waiting and looking forward. I just noticed that is everyone can hear, because I just noticed that my I am unmute. Is everything okay? Oh no.
Yeah, we're hearing you fine.
Okay, sorry. I just, maybe the poster make me confused. Okay, so this is the examples on the one of the project that using the HPC, our small HPC. And our next plan for this project is we are hoping that the platform, as what Kim said, is not really ready yet, but we are hoping that in September we can do the trial run. We just have a visit from the computational chemistry researchers that they wanted to try run their huge amount of data set on this platform. So we are planning, if possible, to have this ready in September. And then if everything fine and stable, and we're going to organize more focus and user workshop based on their disciplines like the engineering, agriculture, and so on. And probably we will provide more awareness on HPC for the beginners, for many researchers in our universities. Okay, so I guess that's all from me for the updates on the projects from Malaysia. So thank you, Andrew, and the rest.
Thank you very much. Unfortunately, we're running a little tight on time. So we don't have time for questions at the moment. If people do have questions, can you please put them in the Hoover application and we'll be able to answer them. Let's move on to our next presenter, Saranjit Kaur Bogal from the Research Software Alliance, who will be discussing navigating the research software engineering community landscape in Asia. Over to you, Saranjit.
Thank you, Andrew. Hello, everyone. My name is Saranjit. I'm based out of India, and today I'm presenting a talk on navigating the research software engineering community landscape in Asia. A bit about myself. I am a community manager for Asia region at the Research Software Alliance. I'm also the lead and co-founder of the Research Software Engineering Asia Association. And this year I got selected as a fellow of the Software Sustainability Institute. This is a bit more about me, which brings me my journey that brings me to open source and open science. I've been part of various open source and open science programs, including Google Season of Docs, Google Summer of Code, the NASA TOPS subject matter expert, and instructor for carpentries. Here is a brief overview of what is and what is not a research software. So research software includes all the source code files, algorithms, scripts, computational workflows that are created during the research process or for a research process. Software components like operating system, libraries, dependencies, packages that researchers use to perform their research that they have themselves not created is not qualified to be called as a research software. It's software in research and not research software. So this is the definition developed by the FAIR for Research Software Working Group in 2021. A brief overview about who creates research software and where is it created. As the name suggests, it's created during and for research by researchers or scientists, sometimes even by citizen scientists, independent researchers in industry labs, academic research labs, by open source project maintainers, volunteers, to name a few. Where is research software being used? So it's used to automate different tasks, to create new algorithms, or to verify existing theoretical results computationally. Here are some good practices to store your research software. So whenever possible, try to store your research software on open source repositories like GitHub, GitLab, Zenodo, so that you can easily share it with other researchers and also have version control of the work that you're doing. Some more good practices like use informative file names, use informative variable names. So instead of using random variable names while writing your code, use informative variable name, which helps you to, which helps your future version. So you're essentially helping you in the future to understand the code that you have written. Whenever possible, do document your code, because say you're writing a code today and 6 months down the line, you might really forget why did you write a certain step in the code. So document your code and use version control systems for storing your code. Another important aspect of research software is its reproducibility. So why it is essential? It's because if your research software is reproducible, another researcher can easily verify your research results. It helps, this helps in establishing authenticity of your research, and also helps in getting more collaboration with the wider scientific community. It also helps in reducing the time spent in reinventing the wheel. So if someone has already done a particular research and their results are reproducible, you don't have to go on and doing the same thing again. It is also helpful to be able to modify a code or to customize it for your own or for specific settings. Another important aspect is licensing of research software. So we mostly talk about licensing of code, but please also bear in mind that it's also important to license your documentation. So for example, whatever non-code contribution you're making, for example, this slide, it's licensed CC BY. So there are Creative Commons license even for documentation, the material that you're preparing. And it's permissive, restricted, depending on which license you choose. Make sure you're documenting your code, documenting your images or research outputs that you produce, graphs and all of that. Now, I've been speaking about research software. So here's a brief definition of who is a research software engineer. So far, I would say for Asia region, or in fact, across the globe, research software engineer is more of a feeling rather than a working title, because there are very few people who actually have the work title research software engineer. And that's because it's still getting recognized within institutes and organizations. So it's a broad term for people who combine programming as well as research skills that have trouble defining the role and value within academia. So some examples are people, researchers, academicians who really love to code, and really coding is the main part of the research work. Generalists who bring communities together, system administrators, software engineers who work within research domain. So all these people could be called as research software engineers. A brief history about the research software engineering movement. This started at the collaborations workshop at Queen's College, Oxford in 2012, where a small group of researchers met and they discussed the lack of career opportunity software developers within academia. And that is when a new role in research emerged called the research software engineer, or the RSC. In 2021, I proposed a project about bringing the Asian community on the research software, global research software platform. So this image is a visualization of my idea of bringing Asia on the global map of research software engineering community. It was built, this association was built through a project in Open Life Science program, cohort 4, where I mostly devised the infrastructure, the website, social media for this association. And then we also continued in the cohort 5 of the same program. This program that I'm talking about is called Open Life Science. It's a program, it's a 16-week mentorship and training program, open to all. So if you have a project idea, if you have a working prototype, try to submit to this program, and there are high chances that you get selected, and they train you, like you get a mentor and help you develop your project idea based on open science principles. The mission of RSC Asia is to promote and build the research software engineering community and profession in Asia region, while also fostering global collaborations. Here is a brief overview of the activities that we have been conducting at RSC Asia. So we organized and participated in the Hacktoberfest event in 2021. That is when we launched our association, and we had community members helping us build our website and do open source contributions. We also organized a workshop on how to write alt text for scientific diagrams. So alt text is the text that you write behind the image. So if someone requires extra help with reading, like images are not that screen reader friendly. So if someone is using a screen reader to read your slides or documents, and there's an image on it, then and it does not have an alt text, then there are high chances that it will appear like a error, like just it will say image and it won't describe what is in the image. So make sure whenever you're using images in scientific documentation, make sure that you're providing an alt text to the image. We also organized the first conference in collaboration with RSC Australia in 2021, and we are also planning to organize one more this year. We again participated in the Hacktoberfest for 2022. Some more current activities at RSC Asia are the monthly community calls. The next one happens on 21st September. And the second online RSC Asia Australia Unconference happens from 13th to 15th September. I'll be sharing the slides, and if you're interested, do register for the Sun Conference. We are also providing scholarships and microgrants for people who need any support in registering. I'm also a part-time community manager for Research Software Alliance, which has the mission of supporting research software and those who help to develop and maintain it, and to bring different research software communities together. I'm responsible for community engagement by sharing information of different initiatives within Asia region, while also taking back news from Asia to the global community. And following Software Sustainability Institute, because they regularly conduct programs, camps that could be helpful for people interested in research software. These are some of the communities of practice and organizations where you could participate as a volunteer or just to see what others are doing. Open Life Science, the Turing Way, RSC Asia, Society of Research Software Engineering, and again, Software Sustainability Institute. I have prepared a short task. So it is about what do you think about research software engineering and what do you think about open science for researchers? So if you're interested, do scan the code and fill in a short Google form. And so a few of the selected submissions get a gift from me. So yeah, that's the task. And why I am at APAN, my objective was to propose a task force, which after some discussion, I realized that it would be better not to create another working group. Instead of that, do also further within the existing working groups to promote research software engineering community within Asia. And I'm open to interested people who would like to contact and help support the RSC Asia Association. Thank you.
Thank you, Saranji. It's really great to see the next generation of software engineers coming up, and particularly leadership coming from ladies in the field. We need more gender balance. Our next speaker is Bimo Tenjo, who will be describing the role of molecular dynamics in drug discovery, and he's from UPM in Malaysia. Please share your screen. Thank you.
All right. Can you see my screen? Can you hear my voice?
Maybe if you could speak a little louder, please.
Sorry. Can you hear me?
Push the volume up, please.
Can you hear me?
We can hear you, but you're very faint. Perhaps you could move closer to your microphone.
Yeah, so you can hear me, right?
That's good now. Thank you.
All right, thank you. So Good afternoon, everyone. I'm Bimo from Malaysia, and today I'm going to show you what I've been doing for the past 20 years. And the reason I'm here is we want to show how dependent we are on HPC. So in my group, we are doing drug design. So our group is working at the interface of synthetic chemistry and computational chemistry. So this is the question that I always ask everyone in my group, that can we trust our results, especially results from molecular simulation? Because as you remember, when we started doing this kind of work 20 years ago, the question asked by people who are doing experimental work is, yes, you can see the molecules on computer, you can see all the simulation, but we cannot touch them. We cannot see the molecule. We cannot touch the molecule. So the question is, can we trust molecular simulation? So the reason why we use computer for designing drug is because the whole process is long and tedious. Yeah. So this is the typical drug discovery process. It might take 10 to 15 years and $1 to $2 billion. And I heard that the cost is increasing now. And the failure rate is pretty high. For oncology, it's around 95%. So that's the reason why we always try to come up with ways to shorten the process and also cut the costs. And using computer is one way to shorten the time and also cut the costs. Whether or not it works, well, that's a different story, but at least we try to make this process shorter with less costs. And during pandemic, we can see that vaccine was sorry. So is the display okay?
Yeah,
How about now?
that's fine. Much better, thank you.
All right. Okay. Thank you. So during pandemic, we can see that vaccine was discovered within 2 years, even less than 2 years, and unfortunately, the same thing did not happen with drug. Until now, we don't really have effective drug for COVID. There is Paxlovid, but the efficacy is questionable. So the same story actually did not happen with drug. So this is something that is quite challenging, and using computer is, we think we can speed up the process to get the drug. So the reason why we use computer is because we want to replace or complement an experiment because of the cost, because of the time. So we thought, well, if we can use simulation to replace those processes, then we might speed up the whole process. And this is not something new, because we use computer to study the collision of stars or galaxies. We use computer for flight simulation, to simulate the explosion, which is quite dangerous. Those who are working in chemistry lab, you would understand how dangerous it is to work with explosive materials. So some of those processes we can actually model it using computer. Or if it's too expensive, if it's too expensive, for example, testing drug on animal is expensive. Right now we can model it using computer, using AI. So computer plays a very important role in drug discovery. And in designing a drug, we use computer to build and display drug molecule, to investigate how reactive the molecule is, because the molecule needs to interact with the receptor, or the molecule might interact with other drugs, because in some cases we take more than one drug. So it's whether or not there are interaction between drugs, we can study using computer. We can calculate the electrostatic potential, we can evaluate the mechanism, we can study the behavior of a molecule, the dynamic behavior of molecule, and etc. So the whole idea of using computer in designing a drug actually stems from this question. We want to know the location of an atom, of the location of electron at a certain time. And normally we use a Schrodinger equation to to know where the electron is. And from there, we can calculate a lot of molecular properties. And this is the equation, and I don't want to scare everybody off, so I'm not going to discuss about this equation. And there are two ways of doing it. First is we use a classical approach where we describe a molecule as a large body, so it moves by following Newton's law of motion, F equals to m times a, or we use quantum mechanics when we are dealing with electron, when we are studying the reactivity of molecule, where we cannot use a classical mechanic, we have to use quantum mechanics to study that. So we are doing both. Yeah. So in designing drug, in designing a molecule, we are doing both classical mechanics as well as quantum mechanics with different purposes. But sometimes, not sometimes, in most cases, the molecule that we are dealing with is big. It's more than one atom. It's more than two atoms. The molecule that I'm currently working on consists of 100 atoms. So in that case, then this is the challenge. So solving Schrödinger equation for multi-atoms is tough. Yeah. So that's why we don't use this equation. So instead, we use approximation. This is the approximation that we use to simplify the system. Is called Born-Oppenheimer approximation. So those who watch Oppenheimer, you know this guy, Born-Oppenheimer approximation. So this approximation helped us a lot. Yeah, and this is the basis of molecular dynamics simulation, where we use HPC to carry out the experiment. So in this approximation, they assume that, not they assume, the approximation says that the mass of proton is much larger than the mass of electron, so that we can ignore the mass of electron. We can ignore the movement of electron. So by using this approximation, so we can use a classical mechanic. We can use classical mechanic instead of quantum mechanics, so that everything can be described using Newton's law of equation. So the equation now is much simpler, much simpler. You can see this is equation that we use to calculate the bond strength, to calculate the angular energy, torsional energy, and also we calculate non-bonded interactions, which consists of Lennard-Jones and Coulomb interactions. So by using Born-Oppenheimer approximation, then everything is doable using the current computer technology that we have at the moment. But in some cases, we mix them. Yeah, we mix QM and MM. So when we study small molecule, less than 100 atoms, we can use quantum mechanics. And if the system is larger than 100 atoms, then we have to use molecular mechanics. So this is the most popular technique that people use to study how a drug molecule interacts with the receptor, how the drug molecule works by doing protein drug docking. So basically, by using computer, we can see how the drug molecule, you can see that molecule at the center interacts with the whole receptor. And this is the equation that we use. This is the equation that put in a computer, and computer will do the calculation for us. So basically, it calculates the delta G, the Gibbs free energy that represent how strong the interaction between molecule and receptor. And from there, we rank the molecule based on how strong they interact with the receptor. And the calculations are based on these interactions. Hydrogen bond interaction, pi interaction, hydrophobic contact, one of the strongest interaction, and it happened, and this interaction happened in all drug molecule. We also consider ligand and protein flexibility, and also we consider the presence of water molecules. And because this technique is so easy and freely available, people publish a lot of papers using this technique. Yeah, and I remember during the pandemic, there are more than 150 papers published using this technique per se. So basically, people come up with a lot of suggestions. This molecule can interact with the virus based on this technique per se. But we have to be very careful, because the whole idea of computational chemistry is based on Born-Oppenheimer approximation, where we neglect the presence of electron. So this is something that I want to bring this issue to your attention, that that doing docking per se is not sufficient. Why people do docking? Because they want fast results, something that can be published quickly. That's one. Second, they don't have HPC. So that's why I'm here to talk to you that HPC is very important, especially in developing and least developing countries. Because they don't have HPC, but the pressure to publish is so huge, so they just do whatever they can to publish something. And this is the solution. Just do a quick molecular docking to see the interaction between one molecule and viral molecule, SARS-CoV-2 receptor, and then voila, publish something. But basically, it's meaningless. But we see hundreds of papers. I'll see you the list of papers in my presentation. So this paper is very interesting. So the idea is we have to be aware of the limitation of molecular docking. And one is we ignore water molecules, because of the, if we include water molecules, then the calculation will be quite heavy for the computer that are commonly available in developing and least developed countries. So normally we ignore the water molecules, so the calculation can be done within minutes. And we can write a manuscript later on. So we ignore the water molecules. This is something that cannot be done actually in actual situation because the interaction between molecule and water has to be calculated. Water contributes importantly in the interaction between molecule and receptor. So we cannot just ignore the presence of water molecule. But unfortunately, when we do docking, we have to ignore the water molecule to speed up the process. Second is we ignore the receptor flexibility to save time, to speed up the calculation. If we have HPC, we don't have to do this. We can model everything flexible, including the drug and the receptor, but because of the limitations, most people, they don't have HPC. They have to do this by fixing the receptor and let the molecule moves, which is not correct actually. Because it brings some serious implication, which I will show you in my presentation. Because if we model the protein as a rigid body, we lose this kind of movement. I'm showing you one example from acetylcholinesterase. So in this enzyme, the protein actually is flexible, and the movement of phenylalanine 330, you can see here, phenylalanine 330 actually plays very important role in the catalytic activity of this enzyme. And by doing simple molecular docking, we cannot see this movement. So the result we get from molecular docking is not accurate. And this is our personal experience with molecular docking. So we published a paper in 2012, so a long time ago, more than 10 years ago. So actually, this is the result of molecular docking versus our experimental result. So what we get, the result we get from molecular docking, we tested in the lab. So we really tested in the lab because in the lab we do both, experimental and computational. So there is no correlation. There is no correlation between the activity of the molecule and the binding energy based on molecular simulation. So we expect there is a correlation, but the actual result, there is no correlation, and the reviewer asks why. And we answer well because when we did molecular simulation, there are a lot of approximation, and this is something that is not very surprising actually. So there is lack of correlation. So this is something that actually becomes a turning point in my career because before we published the paper, I always believe in molecular simulation. I trust whatever computer gave me. Whatever computer gave me, I trust. So when we saw that result, then in our group we made a decision. All result from computer simulation has to be tested in the lab experimentally. So we cannot just rely on molecular docking result and conclude this molecule is good as a drug. We cannot do that anymore. And this is what I mentioned before. During the pandemic, there are more than 150 papers, 168 papers on molecular docking simulation of SARS-CoV-2 and Pro, so the protease of SARS-CoV-2 virus. And from this analysis, none of these papers did validation. So everything is just molecular docking without any validation. without any validation. So after 2 or 3 years of pandemic, there is no single drug from molecular simulation because zero validation. So this is something that come to our attention. So now we change our strategy. So this is where HPC becomes very important in our work. Now, instead of using molecular docking per se, I show you in my previous slide that there is no correlation between docking results and experimental results because we ignore the fact that protein is flexible. Now, we decided in our group, we have to do molecular dynamic simulation to simulate the flexibility of protein. And because MD simulation is computationally heavy, so we have to use HPC here. Yeah. So this is what we are doing now. So we model the flexibility of protein using MD, followed by molecular docking. And this technique is called ensemble docking. And it was introduced in 2018, before 2018 by Jeremy Smith, one of my PhD examiners, Jeremy Smith. So his group introduced this technique, ensemble docking. So basically we have to model the flexibility of protein using molecular dynamic simulation. So this is the flow chart. So we start with simulate the protein. So we get the whole conformational flexibility of protein, and we do molecular docking simulation after the MD. This is what we did in 2017. So we are preparing a manuscript. So by doing molecular dynamic simulation, we discovered something very important that molecular docking was not able to discover this. So we discovered this movement. If you can see this movie, you can see that the blue amino acid is moving up, down, up, down, up, down. You won't see this when you do molecular docking per se. You won't see this. We are able to see this because of molecular dynamic simulation, and this changed the whole story of how we design a drug for PAD4. Because when this histidine 640 opens, we can design a bigger molecule to fit into the binding pocket of this enzyme. And now we are using the same technique to design drug for Mycobacterium tuberculosis. So we are working with people from Japan and also from Malaysia and Indonesia to design drug for tuberculosis. And we are using the same technique, which is ensemble docking. So that's why I'm here. I hope by listening to this talk, we realize that HPC is very important to support a drug design campaign, because we want to model the system, the whole system, drug and receptor, as accurate as possible. And it requires huge computing power. And I hope we can collaborate more between we chemists and computer scientists and people who are working on developing the HPC, and especially in developing and least developed countries. So that's all from me. It's a short presentation, and over to you, Andrew.
Thank you very much. That was really fascinating. Our final speakers for this afternoon, or for this session, are Alex Moira and Josu Lee. Alex is from the King Abdullah University of Science and Technology in Saudi Arabia, and Josu from KAUST in Korea. Over to you guys. Thank you.
Hi, good morning. I'll be doing just a brief introduction to our speaker today, Dr. Josu Lee. I'm from KAUST. We are from KAUST, the King Abdullah University of Shaheen 2, a Cray supercomputer, which will be soon replaced, and then I will leave that for Mr. Dr. Jaisley to speak. And he is our facilities director in the Research Computing Core Labs. So with that, up to you, Jaisley.
Okay, let me share slide. So can you see the slide?
Yes.
Okay, thank you. Thank you for the nice introduction. So my name is Jisoo Lee. I'm a facility director here, and I'm responsible for the HPC, AI, and the visual region services at KAUST. So today I just want a very brief introduction of the HPC and AI activities, focusing on the infrastructure and application. So we have a true system to support the need for the KAUST and even the kingdom. So our flagship system is a Shaheen 2 supercomputer. This has the performance. This has a latent pack performance of 5.5 petaflops. It is powered by about 200,000 Intel Haswell cores. And this is one of the largest all CPU machine in the world. And that's by design, because we just want a system. It's very easy to use. And that strategy has paid off that at this point that we have about 115 faculty using the machine, which might sound much, but actually the KAUST is a very small university. So that's about 60% of faculty. So imagine that your supercomputer used by 60% of the whole population. That is very unusual, I guess. So we have made this system was introduced in 2015, and we have made the improvement both in software and hardware, but there's no getting around that this system is getting old. So we started procurement of its successor, that's the Shaheen 3. So we decided not to worry about the new names, so we just go with the numerals. So in the designing for the Shaheen 3, we start with the workload. So we want to accommodate multiple workload. For example, that what is run on Shaheen 2 at this moment is traditional HPC workload that we want to accommodate that. And also we have to focus on AI workload too. At 2015, it was not too significant, but at this point, I guess everyone in the world, they have to do that. And also, we also feel that, I mean, there was a hybrid workload. What we mean is that even for the single application, they use both traditional HPC side and AI in a single application. So what we decide to do is we decide to go for the single unified system with a modular architecture. So we have a CPU partition and GPU partition. And also, we are trying to provide more ways of the user to access the system other than single batch scheduler. So in terms of the performance requirement, that is, we are focusing on real application performance. So the good thing about KAUST is that we know who is using the machine, and we know who will use the machine, and we know what they do, and we have pretty good idea what they're going to do in the future. So because it's easier to get the requirement, that is just easy to optimize the system for the particular requirement. And of course there's a storage requirement and interconnect. So we went for the open tender and eventually select HPE Cray EX system. So it has a CPU partition. This is about 4600 node, and each one has a 2 AMD Gen 1 CPUs. And it has a GPU partition as about 700 node, and each one has a so-called NVIDIA Grace Hopper super chip. So this is the architecture that so far that if you want to use a GPU card, it is sit on the PCI Express bus, but this is the one that CPU and GPU in the same module. The advantage is that compared to the PCI Express card, that the bandwidth between the CPU and GPU is increased by 7x. So that is a kind of this is a newer technology, and we are the early adapters. So there are 3 institutes in the world that is going to use this chip in large quantities. So us and the CS of Switzerland and the Los Alamos National Lab of the States. So it is kind of the good partner to be in. We are a bit nervous because we are the kind of the first early adapter, so we are kind of guinea pig, but we feel that that's worth the price. So in terms of storage, we have about 80 petabytes of storage. I'm pretty sure it will last a couple of years, and then we have to expand. So the CPU partition, actually, the installation of CPU partition is started. Actually, it's ongoing in the basement. And we are expecting to provide production service by the end of this year. And the GPU partition will come in next year. Then we'll just provide service there. So, okay, and that's we have another system called IBEX. This is kind of the commodity. This is the kind of system my staff built from scratch. So this is you can think of like DIY cluster, right? So it has about 10% of the Shaheen computing power, and it has a heterogeneous architecture, as you can see. It has a CPU node and GPU node and so on. And you might wonder why you need IBEX cluster if you have Shaheen, right? So one comparison is that, so basically there are things that it's not possible to accommodate within Shaheen, or it's not appropriate. So one comparison I can give is that you think like a Shaheen, like a Ferrari, right? So in your house, suppose you have only Ferrari, then if you go to a convenience store, maybe 500 meters away, you don't want to use a Ferrari, you want to use a Hyundai, right? So basically that's why you have to have a have a multiple resource to complement. We feel that's the kind of much easier way of the even the efficient way of meet the resources, meet the requirement from the kingdom, from the Kazakhstan kingdom. So in terms of when we start the procurement of the Shaheen 3, it was a kind of good chance for us to review what has been done with the Shaheen 2. And over his lifetime, it's provided about 7 billion core hours to about 1,500 users. And you can see that the area is pretty diverse. And what I imagine is that it's not very different from any open research computing facilities. I mean, what actually do at KAUST, you might have that this is very special region, but in reality, it's not very different from the, let's say, Berkeley or Korea. So I just want to just give a pretty simple overview of the application. So they kind of classify as a few domains. These are kind of areas that is used more heavily. So I'm going to give just a couple of examples for that. So first example is this is a fluid flow around a racing car. So KAUST has a collaboration with the McLaren racing team. And we have multiple activities there. And one of the activities, the full-scale simulation of the racing car, flow around the racing car. So the goal is that to do the full vehicle simulation, but in a much higher accuracy than what has been done before. So the faculty who are leading this project, that he want to use higher order model for the solving the differential equation. And the collaboration with my team is that then he has to implement on Shaheen 2. So we work together to identify the performance bottleneck. And then we optimize the code and scaling up all the way to the side of the Shaheen 2 cabinets. So that's kind of example that we do for the collaboration. Other example is a seismic. So this is kind of there's an entity in Saudi called Saudi Aramco. That is the biggest company in Saudi and probably one of the biggest company in the world. So they are doing this kind of reservoir simulation. So they want to simulate the oil reservoir of the kingdom. So at that time, the operational model is called mega power. So which means that they divide the kingdom into 1 million cells and do the simulation. Of course, they want to enhance their accuracy. So ambition at that time, this was done about a few years ago. Ambition at the time is that they want to enhance the accuracy by 1,000,000 times, right? So that's what the TerraPower that's aiming for. The problem, they have multiple problems. That one of the problems they have is that they want to kind of test this new idea, but there's no facility in Aramco they can test it. So that's how we come in, that we work with them. They are able to use the whole Shaheen for themselves for a couple of days, but also we help them to optimize the cost. So eventually they validate their code. Then they went to the CEO of Aramco, say, okay, I want a bigger machine. So they got their wish. So they later, when they validate the code, they got the machine that is just used for the seismic for the reservoir simulation. So at that time, this was like 1 trillion cell simulation is the biggest simulation ever done in the world. So it was a world record. And with Aramco, that we have a 3 world record. And so it has been very nice collaboration between them, between Aramco and us. I think that probably I'm just running out of time. So this is another collaboration with the Saudi electricity company. They are the one who is providing electric power to all these houses and factories and so on. And one thing we did is that we are trying to reduce the power loss. So there's something called technical loss and non-technical loss. The technical loss is because of the loss from the production to the distribution, because of the infrastructure, the technical limitation. And all other loss is classified as non-technical loss. And so there, of course, the non-technical loss, you have to focus on how to reduce the inefficiency. And we work with them to identify the source of this non-technical loss. And their way of doing things, that they have chance of they have success rate of 3%. We work with them to increase that to 75%. So by applying this way, this is based on the machine learning for the anomaly detection, then we can just save that about $20 million every year by applying this method. So I know that I'm kind of up to time. So I think I just want to end with about the building communities. So the role that the KSL plays, my lab plays is something between University Computing Center and the National Computing Center. So the eventual goal is that we want to be part of the building national HPC and AI ecosystem. That has 2 components. One is providing infrastructure, and the other is providing community. Regarding the providing infrastructure, we are actually serving about 20 organizations in the kingdom. Actually, we are the only meaningful provider of the computing cycle, computing services. And we also do consulting and training too. And regarding the community, that there's a lot of activities, and one of the notable activities, HPC Saudi. This is annual event. This has been going on more than 10 years. And we are actively participating there and to engage with their communities there. And also we have hosted the event twice. So by doing that, we just want to not only serve the coast, but also the kingdom too. All right, okay, that's the end of my presentation. Thank you for listening.
Thank you very much, Joseph and Alex. This brings us to the end of the Asia Pacific Research Platform sessions in this APAN. We would certainly welcome any of you who have interesting projects you would like to share, or updates from your country, or just anything else you think would be applicable to this group. Please let us know, and we can schedule sessions at the next APAN meeting. So with my co-chair and I, thank you very much for joining us today.